Welcome to the Explainer. Today, we are tackling a massive topic for technical design interviews: synchronous versus asynchronous microservices. Because, look, drawing a bunch of boxes on a whiteboard, that's the easy part. But confidently explaining exactly how those boxes should talk to each other, well, that is the real test. So let's get right into it. So picture this. You've got the marker in your hand, you're sweating just a little bit, and the interviewer drops this prompt on you. They want you to design a system, and suddenly you have to decide the entire communication flow. To make this super concrete for us, we're going to use a fantastic case study right from our source material, building a highly contested vaccination slot booking system. Honestly, it is the absolute perfect high-pressure environment to really test our architectural choices. Okay, let's dive into this. What exactly is synchronous communication? At its core, it's a baseline pattern where one microservice makes an API call to another service, and then it just stops. It sits idle. It waits until it gets a direct response back. It's kind of like calling someone on the phone. You ask a question, and you literally wait on hold, doing nothing else until you get your answer. Now, we immediately contrast that with asynchronous communication. This is a pattern that lets your code fire off a message or a call, and then boom, it immediately continues running and executing other tasks. It doesn't wait around for the response. It totally frees up the system to do other things, basically just trusting that the message will be handled by the receiving service whenever it's ready. To really see why choosing between these two is absolutely critical, let's look at the vaccination center dilemma. Imagine a user frantically trying to secure a vaccination appointment. You've got tens of thousands of people hammering the exact same database at the exact same millisecond. Your system has to handle this crushing load without buckling. But even more importantly, it has to be perfectly 100% accurate. So this right here is the critical path. The user requests a slot, the system checks the database, the slot is officially blocked, and finally, a success response is sent back. As our source points out, this specific path absolutely must be synchronous. Why? Because you simply cannot risk a data mismatch. Just imagine the absolute nightmare scenario of using an asynchronous call here. You'd essentially have a user request a slot, and you immediately send back a booked message just so they don't have to wait, but then the backend catches up and realizes, wait, no slots are actually available. You've just given them a false confirmation. No way. For strict data verification, the user literally has to wait until the database confirms that slot is actually theirs. But of course, that strict verification comes with a pretty major downside. Synchronous systems are what we call tightly coupled. Because service A is waiting on service B and service B might be waiting on service C, they're all chained together. If the slot availability service crashes, well, the entire vaccination center application fails to respond to the user. The risk of spreading failures across multiple services is incredibly high with this setup. So how do you patch up these synchronous weaknesses on the whiteboard? You're going to need two main things: service discovery and replication. Instead of just having one single slot availability service, you spin up instances 1, 2, and 3, all holding replicated code. Then you slap a load balancer in front of them. That way, if one instance goes down, the load balancer just shifts the traffic to the others. It keeps the system alive for sure, but keep in mind, the underlying services still remain tightly coupled. But what happens after the database is locked? Now we hit the secondary path. The slot has been successfully confirmed. Next up, the system needs to send an email and a text message to the user with their appointment details. And you know what? This is the perfect time to switch over to the asynchronous pattern. The user absolutely should not be blocked from going about their day just because your email server is taking 10 seconds to respond. By using an asynchronous setup here, your architecture becomes loosely coupled. And honestly, this is the breakthrough moment. The booking service simply drops a message into a message broker saying, hey, send an email to this user. And that's it. It doesn't sit around waiting for the email service. If the email service happens to be down, it's not a disaster. The message broker just holds onto the task, and once the email service boots back up, it pulls the message and sends the notification. The user's booking experience was literally never disrupted. So the crucial point here, and this is exactly what interviewers are testing you for, is understanding this ultimate trade-off. On one side, synchronous communication guarantees data consistency. You know exactly what state the system is in before you respond. On the other side, asynchronous communication unlocks high scalability and resilience. It gives you so much better control over isolated service failures without accidentally taking down the whole application. You're going to want to take a mental snapshot of this matrix. It's basically your cheat sheet. Synchronous design is simple to set up using standard REST APIs, but it's tightly coupled, and as we saw, it can spread failures. It is absolutely best for strict data verification. Asynchronous design, on the other hand, it definitely introduces architectural complexity, but it's loosely coupled, highly resilient to failures, and it's best for things like alerts, logging, and reporting. Keep this mental model handy. It's a lifesaver. When you're standing up there at the whiteboard, you want to vocalize your strategy really clearly. I highly recommend using this exact golden rule of thumb. Start simple with synchronous, scale up with asynchronous. Our source material heavily emphasizes this point. Introducing asynchronous communication from scratch when you're just starting to design an application, that introduces massive, unnecessary complexity. You always want to optimize for the speed of application evolution first. So that begs the question, how do you actually map this evolution out on the whiteboard without creating a chaotic, confusing mess? Let's look at the exact steps. Here is your 4-step interview checklist. This takes you all the way from a blank slate right up to a fully decoupled architecture. Let's break down steps 1 and 2 first. Step 1 and 2, start and stabilize. You really want to explain to your interviewer that building multiple components from scratch that communicate asynchronously is just a complex nightmare. Actually, scratch that. It's a trap a lot of candidates fall into. Instead, you build the core interactions using simple REST APIs. This avoids early architectural complexity, it proves the core logic works, and it optimizes your development speed. Even if you're dealing with a legacy monolithic platform, you start synchronous so you can fully understand the pieces before you try to break them apart. Now, steps 3 and 4 are where you really get to show off your architectural chops, and this brilliantly illustrates how you evolve the system. Once the core system is stable, you tell the interviewer you're going to audit the communication paths. You're hunting for any process where an immediate response isn't strictly necessary for the user to continue, like logging, emails, or SMS. You then decouple those specific paths using message brokers. You can absolutely name-drop tools here like Kafka for a pub sub architecture or ActiveMQ and RabbitMQ for point-to-point queues. Doing this instantly improves your system's overall latency. Ultimately, a great architect knows when to use a tool, making the right trade-offs to protect the system. You now know the when. But listen, if you introduce asynchronous events, you also introduce a brand new problem, event-driven chaos. So, how exactly does a tool like Kafka manage millions of decoupled events without losing a single one? Well, we'll leave that mystery for you to explore next. Thanks so much for joining me on this explainer.